Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking at second order reactions. So in these cases, we're just taking our dependence upon the concentration for a reaction. Again, this case, the generic A goes to B, and we're upping it up a little bit, as now the rate will depend upon the square of the reactant concentration. And as a result, this is really going to increase that concentration dependence, and our rates are going to vary a lot more than we saw before. So one of the big things that we're going to see is because of the square nature, this means that our reactions tend to go very quickly at high concentrations and very slowly as we ramp the concentrations down. Because again, that rate has a much bigger variance. And so we can go ahead and see this with our overall rate equation, where the decrease of the concentration of A now is amped up by this square of the concentration. Now let's go ahead and see what this looks like in terms of integrated rate laws. So we're going to go ahead and take this rate expression and integrate both sides from 0 to t, both in terms of time and in terms of concentration. So one of the interesting things here is that, again, the left-hand side is still kT, but now on the right-hand side, this gives us the difference in between the inverse of my final temperature, and then now we're subtracting out the inverse of my initial concentration. So again, this is going to be a little bit less intuitive as we're now working in inverse concentrations. However, as usual, we're going to try and rewrite this expression to solve in terms of our final concentration. So we now see here is that the inverse of our final concentration will be equal to a notable exception here, plus kT plus the inverse of our initial concentration. And one of the reasons why is that it's important to remember that as the concentrations get smaller and smaller and smaller, the number will get bigger and bigger. And that's why we see this plus kT for a second order reaction, but not for 0 and first. And again, this is going to be our second order integrated rate law. And just like previous, it means we can go ahead and obtain information such as our rate constant by plotting a straight line. So one of the classic cases that you find in a lot of second order reactions is the dimerization reaction, where you have one reactant or monomer, and it can go ahead and react with itself to produce a new product, in this case, a dimer. And this reaction is kind of fun as it goes from red to colorless. So it's easy to track that concentration of our reactant. And now what we can do is take a look at how this concentration of our monomer changes with time. We see this big steep die-off. But qualitatively, it's a little hard to differentiate from a first order reaction. So how we can go ahead and do this is by plotting the inverse of our concentration versus time. And we should see this nice straight line. And so doing this, what we can go ahead and is manage to pull out our rate constant for the reaction, as that should just be the slope of this plot. And it's also possible, if you know the exact amount of time elapsed, you can also back out the initial concentration if you know the final, or vice versa. And so this is a very useful piece of information. And so again, one of the big features we're seeing here is that qualitatively, this looks a lot like a first order reaction, but numerically, we start to see some big differences. And this is really amped up when we look at the half-life. So again, just like before, we can try and determine the half-life of reaction by substituting the time for the half-life, and the final concentration is just half of the initial concentration. What's a little bit interesting in this case is if I plug in the initial concentration over 2, that's the same as in this case having 2 over the initial concentration, again, due to the concentration being in the denominator. So now what we can do is say that, all right, I have twice 2 times the inverse of my initial concentration equals kT plus 1/2 A naught. 1 over A naught. And now we're going to go ahead and move all of our A naughts to one side. And by that, we now know that 1 over A naught is just equal to K times the half-life. So that gives us a half-life of 1 over our rate constant times the initial concentration. And so this is something that is a little bit interesting, as to a certain extent, it kind of resembles what we saw with zero order reactions. We now have a concentration dependence for our half-life again. The biggest difference here is that for zero order reactions, the half-life essentially got shorter and shorter as the concentration went down. Here, it turns out that that rate slows down way more than the concentration decreases. So what we tend to find is that for second order reactions, they have relatively short half-lives at the original high concentrations. And as the reaction goes on longer and longer, we tend to see this half-life essentially increase. So for this dimerization reaction, we see that the half-life is originally just under 40 minutes, and now it's a little bit over 40 minutes for the second half-life. And when you go to the third, it's a little longer yet, and this keeps going. And so this is a very important feature to look out for in second order reactions. Unlike first order, we tend to see much longer half-lives the longer the reaction proceeds. However, one of the other things that should be acknowledged is a very special case of second order reactions. And this is called a pseudo first order reaction. So this is a second order reaction where the concentration, the rate depends upon a squared concentration, but it's a little bit different because it's no longer the concentration of A times the concentration of A. It's the concentration of A times the concentration of B. This is how a lot of chemical reactions proceed. I mix two reactants and the rate's dependent upon both of those concentrations. So this sort of reaction is said to be first order in A, first order in B, but second order overall. So a good way to think about trying to figure out overall orders of reactions is remembering that each of these concentrations of A and B has a coefficient of 1. And to figure out the overall order, you just add together these exponents. So in this case, it's 1 plus 1. So we have a second order reaction. And we can go ahead and confirm this by taking a look at the units for our rate constant. So we know that the rate should be in molar per second. And now here on the right, we have molar times molar. So to make the units work out, the rate constant has to have units of per molar second. And this is the same sort of units that we have on a second order reaction. However, one of the things that is worth noting is that it can be a little hard to try and determine the rate constant for one of these second order reactions. So typically what you do is you don't try and let both concentrations of A and B change at the same time. You set up the situation so that only one concentration changes at a time. In this case, what we can do is set the concentration of A so high that as B reacts, it doesn't make a noticeable difference in the amount of A present. So when you do this, the concentration of A stays relatively fixed. So what we're really seeing is how the rate changes as a function of B, because we now have a new observed rate constant, which is going to be relatively constant, as the actual rate constant is, well, a constant, and the concentration of A really isn't deviating from its initial. So using this sort of pseudo first order rate reaction, where it isn't true first order, but it acts like it's first order in B, we can go ahead and treat this as a first order reaction in B. So we can go ahead and track how the concentration of B changes with time and use this to find our observed rate constant. However, from here, I need to try and back out from my observed rate constant to figure out the overall rate constant. This can essentially be done by taking my observed rate constant and dividing by the concentration of the species that is essentially in excess. So one of the things that is worth noting is there are better ways to try and determine this overall rate constant, but it mostly includes using multiple concentrations of A so that you have as much statistical robustness in figuring out that rate constant. So let's go ahead and try and find a real application of this sort of reaction. And it turns out we've done one of these in lab. So it turns out crystal violet is a nice, beautiful violet color that essentially goes to clear when you add sodium hydroxide. And this has an overall rate of reaction that is the rate times our rate constant times the concentration of OH times the concentration of crystal violet. But the concentration of crystal violet is going to be usually fairly low, on the order of 10 to the negative fifth. In contrast, if I go ahead and set the system to having a 0.1 molar concentration of sodium hydroxide, turns out that observed rate constant will stay fairly static. And thus, I can go ahead and figure out what my observed rate constant was by watching the change in the concentration of crystal violet. And then using that, once I know my observed rate constant, I can back out the overall rate constant. So we've covered a lot of different types of order reactions. Next time, we're going to go ahead and do a quick compare and contrast, seeing how these different types and orders of reaction compare to each other and how you can figure out which one is which. Until then, take care.